In this video, we're going to look at counterions in organic chemistry and how I generally go about thinking about them. So we have our notes in front of us. Okay, here we go. So lecture 83, right? Okay, so counterions. These are anions or cations used to counter / neutralize a charge on if it's the case of an anion, it's going to counter a cation. In the case of a cation, it's going to counter an anion. Okay, so for example, what we use them for is typically the nucleophile is not always, but is often an anion. So we write nuc with a negative charge. Now, here's the deal. We can't just have negative and positive charge things sitting in bottles that we pick off the shelf. They will find ways to neutralize themselves, okay? Either soaking up water or hydrogen atoms. It's just difficult to put charged species into bottles. So it doesn't come as a free anion, okay? Instead, it's countered by a positive element, and it could be multiple elements. So it's going to be countered by some positive element, and for us, that's going to be lithium plus, sodium plus, potassium plus. These are all really good contenders. Could it be other things? Sure, yeah, no problem. But sodium, potassium, and lithium, these are the ones that we're going to see for the most part. Now, what's great about this is the salt, that is the combination of counterion and nucleophile, will dissociate in solvent to give the free ions. That is to say that if we take our NaOCH3 and we put that into some solvent that's appropriate for the SN2 reaction, these things will actually float around as Na plus and OCH3 minus. Now what's happening is the ions that are now free, are forming usually dipole ion interactions with the solvent molecules. And so that's why we need to be careful about the thing that we put over the arrow, even though it doesn't influence what directly the atoms that are incorporated into either one of the products. It does influence how easy it is for the nucleophile, which is often a salt, to dissolve in solution. And when it dissolves, the ions separate. And when the ions separate, we now have this free negative charge that is able to do the SN2 reaction. So I'm just going to write free negative. And I'm going to turn the page on my notes and mention that when the nucleophile is free of its counterion, which in this case was Na plus, the nuc minus can react with the electrophile. And that's what it's all about, is combining the nucleophile and the electrophile. And in this case, the electrophile is our haloalkane. Okay, What all this kind of means is that you get to ignore the counter ions. You just kind of cross them out and say, well, it's going to dissociate. It's just kind of, the sodium is there, which is Na, is there just to counter the negative charge on the OCH3. And what I want to do is, I want to just sort of recognize that. So NaOCH3, what you do is you recognize that this is a counter ion. And when you put it into solution, into the solvent, it will dissociate. So I'm kind of rewriting the chemical reaction that I wrote on the back page, so OCH3. So now we have our free anion to do the SN2 reaction. What I haven't shown the SN2 reaction. I've just shown dissociation in the event that solvent is present. Now what I'm getting at is what I want you to sort of have a knee-jerk reaction about is we could just cross out the counter ion and replace it with a negative charge. We'll let the Na plus, the sodium plus, float away and do its thing, but that'll release the negative charge for us to kind of mess around with. Okay, so the Na plus floats away to release OCH3 minus. That is to say, if I've got this reaction, now what I want us to be able to do, and we can't do it yet based on what I've told you, we can't do it yet, but what I want us to be able to do is look at an SN2 reaction without the products drawn and both propose a mechanism and predict the products for that reaction. Now to do both of those things effectively, the first thing I want to do is cross out the Na and replace it with a negative charge. I'm just going to do that in a different color. Sorry, hopefully. I'm going to redraw the exact same thing. So I'm going to cross out the Na and replace it with a negative charge. I'm letting the Na float away as Na plus. The Na plus is gone, so now the negative charge is released. That's the same as saying the Na floats away, and we now have OCH3 with 3 lone pairs of electrons, giving, if we have a bond between oxygen and carbon, now the oxygen has a -1 formal charge. So we have these things float, we have the Na floating away, and that can allow us to predict the type of products that are being formed. So this is going to be really important going forward in this unit. And remember, I said it could be Na, lithium, Li, or potassium, which is K. If you see them, replace them with a negative charge on whatever our nucleophile is attached to. And maybe I should be consistent. It could be an R group, but let's make it NuC. Okay, let's practice this. So if we've got this, let's get some really big things here. This, this, this. What I want you to do for these is cross out the, and I'm just going to move them over to another page of notes here. So you want to draw the structure where you've crossed out the counter ion and replaced it with a positive, or excuse me, a negative charge. Okay, so let's go ahead and do that. Now sometimes these things, sometimes folks draw a bond to the counter ion, particularly in the case of lithium, because it does form kind of a more covalent bond than ionic bond, but we still want to consider the dissociated form if we're going to understand the reaction. And some would say, well, actually lithium's not a true salt, so it actually, we should draw that covalent bond and think about the mechanisms differently. And that's fine. If somebody really wanted to go down that path, that's okay. It's complicated, and it's sometimes just easier to cross out. In this case, the metals, because the metals are on the left side of the periodic table. If you haven't seen the periodic table, if you haven't talked about that aspect of the periodic table before, just recognize these elements are all metals. They're on the left side of the periodic table. We're going to cross them out and replace them with the negative charge on the element that they were attached to directly. And this is a really simple way of thinking about how the counterions are acting, and it allows us to simplify things. Once we know where that negative charge is, as we'll see in upcoming lectures, we'll be able to do the SN2 reaction a lot more effectively. When they're covered up as the counterions, it makes things a little bit more complicated. So, just kind of recognizing them. This was one that we looked at in the past lecture. What we have to do is cross them out and replace them with a negative charge. And that's actually the same as C triple bond N, negative charge. Okay. What I want to just mention briefly, well, let's save it for another lecture. This is a good stopping point. So in an upcoming lecture, we'll look at solvents in the SN2 reaction, which I alluded to their importance in this lecture, but we'll get to more specifically in an upcoming lecture.